In the previous segment, we talked about the state of stress which develops under the case of pure torsion. When we twist something, what sort of stresses they get developed. Now, in this segment, what we are going to discuss is about the deformations which actually happen, and because of which the stresses are developed the way they develop. Okay. Now, when I said deformation, what exactly I mean is, see, suppose you we are first going to discuss some conditions that must exist when we have torsion, that is pure torsion. Okay. So, that means here we have T and here we have T. So, this is our canonical configuration, and then the first condition is any cross section. So see, the other conditions are anyway intact, like uniform cross section, same equal and opposite torques exist acting on this, and cross section is axisymmetric. Now, under such condition, our claim is that all the sections before wherever they were, after the torsion they will not move axially. That means, suppose there was a section here, so I will call it section A, and a section say B here. So, they were there at a distance say x and a distance y from that side. Now, before we applied the twist, and now what we did, we applied the torsion. Then our claim is that these sections will just at their own location they will rotate, but they will neither move forward nor backward. Okay. That means this y will not change to more than y or less than y. Okay. Now, how do you prove it? The logical way to prove is, see, suppose you assume that the section B has come here after torsion. Okay. Suppose B prime. Okay. Now, and just assume then that you are maybe sitting here, okay, and your friend is sitting here. Now, you are looking from this side, okay, you are looking from this side. So, what will be your way of expressing the total event? You will say that I am applying a torque which is clockwise, and as a result of which the cross section B came forward or came towards me by certain distance, say dy. Okay, suppose this distance is dy. Okay, so that means it will tell you that it has come forward. Now, you think about this guy. So, how will he express the situation? He will again tell that the torque is again clockwise and the same amount T as it was for this person. So, he will tell that the section actually has moved away from it. Okay. So, both are expressing about the same section, and both are talking about the same type of torque which is acting, but for one person it is coming forward and the other person it is going backward. Okay. So that is what is an inconsistency which cannot happen, and that is why all the sections will remain as they are. Neither they will move forward nor backward, they will just rotate at where they are. Okay. And then this is true for any circle which you think about at that, sorry, bad drawing, at that particular cross section. You consider any circle on that section, the same thing will happen. So neither it will move this side or that side, they will simply rotate. But then it may, so or shall I ask like this, is it possible that all these circles will rotate by different amounts? Okay. Now that also is not possible, because if that happens, what a condition which can arise is, if you have drawn a diametrical line before the twist is applied, suppose a vertical thing like this, after twist it may so happen that it will go something like this maybe, right? Now if it turns like that, again the same kind of inconsistency will happen from the perspective of this person and this person. So this guy is telling that I am applying a torque clockwise and the diameter is becoming like this, and this person will tell that the diameter has changed to this shape. So now for the same diameter both things cannot happen, because for both of them the loading condition is exactly the same, right? Now you may be thinking that one doubt, that maybe the distance is playing a role, and for example in the previous case when I talked about the movements, you could think that because the distances are at different or the sections are at different locations, so maybe at this location it is moving this side, this location it is moving that side, and as a whole this thing can be explained. But no, the situation is not that. See, if you take a cross section at any point, the torque acting is same, right? So that you can do by cutting it at a particular location and drawing the free body diagram. Suppose I cut at B, okay. So if I take B or this segment, so this side the torque T is applied. Now here what should be the torque to keep the whole thing in balance? That also must be T only in the opposite direction. So it doesn't depend where you are, the application of the same torque is happening, and then this is exactly the same as that of your axial loading. So when you had this F and F, any cross section you pick, the same force was acting, right? So otherwise they will, if you take this as a free body diagram, there will be no balance. So that means at any location you pick, the force F is acting, and exactly the same thing is happening here. So this torque which this person is talking about from his perspective, he is talking about actually this torque which is acting at the section B, and he is telling that because of action of that force or torque clockwise, it is coming or going away from me. So that is where the inconsistency is happening, and same way for this the diametrical thing. So from this what we conclude is all cross sections, they remain at their axial location where they were before the twist, and the diameters remain straight after that twist also. That means all these concentric circles, they rotate by the same angle. Okay. If 2 degrees, if this outer circle has rotated by 2 degree, the innermost circle also would have rotated by 2 degrees. Okay. So that's the, otherwise this kind of inconsistencies will happen. Okay. So that is one of the major things which, or major concepts which I wanted to discuss about the deformation. And using this, what now we can do is we can now quantify things a bit more. Suppose you have, so let me attach this to even a wall somewhere like that. Okay, so that it is fixed to the wall, and now you are twisting by applying a torque T. Okay, so obviously the wall also is applying the same torque T from the other side, and then it is the canonical form. And now you think about, a line like that. Initially, suppose it was here A and B, and suppose the center is here, and yeah. Now, once you twist it, what has been observed is this point, suppose, has come to this point. Okay, so B dash, that means now, okay, so yeah, so this is the B dash point. So that means the angle of twist at this location is, say, phi. Okay, the cross section at the end, and let me call this full length of the thing, the shaft, to be L. Okay, and as we discussed just in the previous slide, that these lines will remain straight. Okay, because every location turns by the same amount. There is no other way out. So that is why this straight line, which was earlier like this, now it will just move to this one. Okay, because this circle, if you consider, this full circle has been twisted by an angle phi. Okay, and similarly, if you go to a slightly inner circle like that, maybe, say if you see this circle, it would have twisted by a little less amount, so like that. Okay, because this C point, if I call, it would have come here. Okay, so like that. And then that is how different segments have different angles, and that is how we say that this phi is proportional to the torque that you apply. Okay, means for the given length, suppose everything else is same, the same material, the same shaft, the same length, everything. If you increase the torque, this phi at this end will keep on increasing, means linearly. Okay, it's proportional to the torque, and this phi is also proportional to the length. Okay, that means if you increase the length, this phi at the end will be more and more for the same torque that you apply. Okay, so that's the situation which we are in, and then we will define the shear strain here. Okay, Okay, so for that what we can do is basically this angle is, so this is the shear strain gamma, because you think of I'll draw another maybe straight line like that, or I'll pick one segment like this, another segment like that, and I'll draw here just like this. Okay, so think about this square sort of thing. Okay, so before the twist is applied, that was looking like this, a square. Okay, now when you applied that twist, what has happened is, this has become, I'll draw with blue, it has gone here. Okay, so now you have like that, and this angle is gamma. Okay, so that is how we define the strain. And because how did we define the shear strain? The angle or the reduction in a 90-degree angle. Earlier this was 90 degree, and now this has reduced from 90 degree by this angle gamma. So this is that shear strain which we wanted to define here. And in terms of that angle, if you want to write this length, see, gamma times L will be equal to, say, this, suppose this point is a rho, rho times phi, right? So that means from here you can just say that gamma is rho phi over L. Now what this tells you is, as you suppose L is constant, okay, you have kept the length of the shaft to be constant, then you think about different rho values, different radius values, right? So what you are observing is it is increasing as you are moving away from the center towards the circumference. Okay, that means if the maximum radius is say C, okay, so here just assume that this cylinder which I had drawn, it was just a part of another big cylinder, and I had drawn like that. So there was a bigger cylinder, and I was considering a generic cylindrical portion whose radius was at, say, rho. Okay, so you can think of like the all discussion like that, so that you can now say that this full radius is C. Then what you can that means the gamma max, gamma max which will happen at rho is equal to C, and that will become phi over L, and this phi will not change because again so whether you are every circle turns by the same angle phi, so that is why this will not change. So this is the maximum shear strain which you will get on the circumference of the shaft. So from there you can actually get a relationship between the gamma in terms of rho over C times gamma max. So, these are some things which you should always keep in mind. One is, this is the shear strain is proportional to the angle phi if rho and L are constant, and similarly from where, I mean, if you, the twist angle is constant and the length is constant, then you have the relationship between, you know, the gamma at any radius rho varies like this in terms of the maximum shear strain that happens at the surface. Okay. So, this is the relationship which we will use in the next segment to in fact come up with the stresses which exist, and we will correlate the torque that you apply and the stress that gets developed, and this will be our basis for developing such relationships. Before I just stop this segment, one more point which I think should be told, no, not this, is, see, here I said that two conditions. One is plane section do not move forward or backward, and their diameters remain a straight line, okay, after the twist also, and that actually is a condition which is valid when the cross section is axisymmetric, and when that happens, the surfaces which are planar before twisting remain planar after twisting also. Now, as soon as you deviate from the restriction that the cross section is axisymmetric, this condition does not remain valid anymore. So, then what happens is this cross section will be warped around. You will what you can do is you can take a eraser, a rectangular eraser, and you know, suppose a long, you go to the bookshop and buy a long rectangular eraser, then draw some rectangles on that eraser like that, okay, full rectangles like that all over the thing, and then you twist it. What you will observe is these lines, you know, use a different color, these lines will no longer remain like straight lines, they will become, you know, wrapped like that, something like that. So, cross sections will completely be warped around. So, which if you can buy, I do not know whether it will be available, if you can buy a circular eraser and do the same thing on this, you can clearly see that these lines which you have drawn on the circle, they will remain as circle, they will not be distorted, but for a rectangular eraser these things will be warped. So, that means plane surface, plane sections will not remain planar after you apply the torsion. So, that is a consequence of these two observations which we had made, but I thought I should make it explicit. Yeah. So, we will stop here with this expression for the variation of the shear strain with respect to radius, angle of twist and the length, and we will see you in the next segment.